Okay, so we're going to be talking about microkernel architectures. Okay, so what is a microkernel architecture? How on earth did we come up with this name? Well, we're going to go back. We talked about in the first week this idea of there are quality attributes. And we need to consider quality attributes when designing an architecture because we need to ensure our architecture is going to deliver those quality attributes. And so a quality attribute is simplicity. Oh, note, you can't use simplicity as the basis for picking your project for the presentation. Can't be simple. But simplicity is sometimes a valid architectural requirement. We're focusing on this needs to be simple. And so we talked about the monolithic architectures and layered architectures and pipeline architectures so far. And so monolith and pipeline are simple architectures. That pipeline has a very simple focus on how things work. It's got a simple interface that allows any process to pick up something and do something with it and pass it on. So it's a really nice, simple design. Monoliths are simple design because everything's encapsulated in the one place. Modularity is then a quality attribute around the design quality. And so layered architectures were introduced as a mechanism for enforcing modularity in your design. Pipeline forces modularity into the design. So these are architectures that try to support those quality attributes. So now we want to move on and start thinking about extensibility is another quality attribute that I've got a software system I'm building and I want to build it up in stages over time. I want to be able to keep adding to it. And so I want extensibility to be a focus of the architecture so it supports extending the software system over its lifespan. So we've looked at monoliths, we've looked at layered, we've looked at pipeline. How well do they support extensibility? Monolith, not so much. When it's small, it's extensible. But if we want this thing to grow over time, it gets more and more complicated. And what tends to happen in monoliths is that as they grow over time, they become more and more degenerative. They have more and more compromises added to them in the design process. And so they get harder and harder to extend. Layered. Oh. I want to extend a layered application, I've got to touch all the layers typically. Most things is I'm adding new functionality. Well, I need to add something to the user interface, and then to the business logic, and then to the storage logic, and then add new stuff into the database and new database tables and things. And it's like, yeah, this is not so easy. It's done frequently because layered is actually a common approach in designing applications, but it means you've got to touch all layers to typically add stuff in. So it's not overly supporting extensibility. Oh, pipeline. Yay. Extensibility. It's just build a new process, throw it in, it reads something, and it passes something on. So conforms to an interface. So pipeline is easily extensible. Another quality attribute is interoperability. So we want our software to be able to work well with other components or systems. We want to easily exchange information with other systems. We want to easily work with other things. So how well do monolith and layered and pipeline support interoperability? Well, with a monolith, interoperability, if it's inside the monolith, it's there, it's accessible, it's easy. write a new component and it's part of the monolith and I can access and use other components. If I'm talking to an external system, not so easy, because I've got to build stuff to talk to that external system, and then everything else inside the monolith has to now work with this new interface to the external system, which is the nightmare side of it. Layered internally, again, if we're following the layered architecture, we talked about the nearest neighbor principle, which is you only are talking with one other layer, and the downward notification principle is it's only in one direction. So interoperability internally, again, is really well supported with a layered architecture. Externally, it's again the same problem as our monolith, in that I've got to build my interface to talk to the external thing, and then typically everything within one layer, and that's the best case, has to now be redesigned or modified to work with that new interface. So it's not so great. And pipeline assumes everything's on the one system. Distributed pipelines are not things we tend to want to do. So we tend to say, nah, let's not try interoperability with the pipeline architecture. So if I want simplicity, extensibility, and interoperability as my design goals, that's where microkernel architectures come in. So with microkernel architecture, why do we call it microkernel? Is because there is a kernel or core to the system. And it's micro in the sense that it's basically, this is a small package that represents the key ideas or key functionality of the system. Everything else is provided by what we call as plugins. So plugins provide the services that then give me the extended functionality of my system. And so the plugins provide all of the interesting behavior. The core system just manages the basic core internal data. And then to make this simple and extensible, we have a single plugin, or sorry, we have a single interface for those plugins. So you have as many plugins as you want, but they all talk through the same interface. And if they all talk through the same interface, we've now got our simplicity. We can have as many plugins as we want. So we've got our extensibility. So we've got mechanisms to support what we're aiming for. Oh, and one other thing, which doesn't appear in a nice simple architectural diagram is, and we need to know what these plugins are. So the core system needs to know what plugins are there, so we can actually use them. And so that's this registry. So the registry keeps track of what plugins are available to the core system, because a key aspect of this microkernel architecture is it's composable. That I can install the core system and then the plugins I want around it. And someone else can install the core system and a different set of plugins and get different behavior from the system. And so it's a composable system, so we need this registry to know which plugins are available, so what services are available to deliver the functionality of the system in this particular instance. So with those plugins, there's two basic strategies. One is that we have the simple approach is all the plugins are loaded statically when we start the application. And so that makes life easy because the registry just sort of says, here they are. And then they're all inside the application. And then I can run the application and have easy access to these plugins. The more sophisticated approach is, well, we load the plugins dynamically. So I can add a plugin at any stage while the core system is running, and it will then pick up that the plugin is available and then make that functionality available inside of the application now that it's been loaded. And then you would have a mechanism to unload plugins when you no longer need them. So it gives you a much more sophisticated environment at the complexity of a much more, well, reasonably complex registry to be able to allow notification to load, and then notification to unload and unload, and then query the plugin to say, what can you do? So I can then tell the user that these things are available. So what system actually uses a microkernel architecture? What's an example of a microkernel architecture? Yep. So VS Code, yeah. Any other examples? So yeah, they're sort of doing different things with that in an operating system. So some operating systems follow the microkernel architecture. And Google has a nice experimental operating system that does, but others not so much as in terms of the actual microkernel architecture. Oh, okay, yeah. So that would be another one. Web browsers. They're getting much less micro in their core functionality. But particularly originally, when Mozilla was really starting, that was a key characteristics of the Mozilla browser's architecture, was as a microkernel architecture that you had a page rendering and retrieval system, and almost everything else was provided via plugins. So another characteristic we want from a microkernel architecture to maintain simplicity is what we call the independent plugin principle. So plugins are independent of each other. They should not talk to each other. They shouldn't have any dependencies on each other. That everything should be coordinated through the core system. Because as soon as my plugins start talking to each other and using each other, I'm now getting a really complicated mess in the design of how I'm going to have to understand things, because it's now, oh, my core system uses plugin 1, but it uses plugins 5 and 12. And I might make changes to 12, that's going to have impacts on everything else. And so it makes life a whole lot more complicated. So we need to keep the plugins independent. They're self-contained units. They do their own thing. They don't rely on any other plugins. They also don't rely on the core system, that they only deal with the core system via its interface. So the core system publishes this interface, and then the plugins implement it, and then the core system can talk to it, and the only communication is via that interface, and the only communication is via the data defined in that interface. And so we're minimizing the coupling or dependencies between the core system and the plugins to what's defined in that interface. And the plugin shouldn't rely on any internals of the core system, only on the published interface. So does having a plugin architecture equate to being a microkernel architecture? And I'm getting no shakes. So IntelliJ is my favorite hobby horse of, it's a massive complex beast, which has plugins, but it's definitely not microkernel. It has a vast amount of internal things. Plugins are a useful concept to add into many other systems, not just the microkernel architectural approach. Eclipse is designed in the opposite of IntelliJ. So Eclipse is another IDE, and it's again based on a very minimal core with plugins. And you can get Eclipse that supports 1,000 different development environments. And it's probably is over 1,000 different development environments supported by Eclipse. So I've seen things like, here is some application. Here's an Eclipse IDE customized for building our application or writing extensions to our application. There's a local company who have built a bunch of Eclipse plugins, and so they've turned it from being just an IDE into actually a code generation tool. And so Eclipse then generates most of the code for their applications. They don't write the code themselves, all done by using the Eclipse microkernel plugin architecture. Now, we said plugins are independent of each other, and they only communicate with the core system via a simple API. Which means that any persistent data that your plugin needs to store needs to be stored within its own database. So it shouldn't be storing stuff in the system database. It may be manipulating data. It passes back to the core system, which the core system stores because it's actually the core system's data. That's fine. But if there's plugin specific data that needs to be stored over the long term or needs to be saved in some fashion, then your plugin has to have some persistence mechanism. Could be a full sophisticated database. It could be some simple files that are stored somewhere. But if there's any persistent data that your plugins have to have themselves, each one manages its own data persistence in its own way and separately to all the other plugins. And then we mentioned we were going to talk about distributed. It's an API. The simple way of implementing your microkernel architecture is that they're statically loaded, and we have a compiled interface, and we just have instances of objects and send messages of objects, or send messages to the objects, which we instantiate within the application using our static loading. But these things could be dynamically loaded. These things could be running on separate devices. And so I can have plugins running somewhere else, but then I need some communication protocol to talk to it. And so we'll mention REST because that's going to be our favorite protocol for the course. But there's all sorts of other mechanisms you could use to talk to those external plugins. Which then leads us to an adapter pattern. Because sometimes I want to use something that already exists as a plugin. But if it already exists, I'm probably not going to be able to make it implement my core systems API. But what I can do is then have an adapter. So I've got this system that already exists that I want to use as a plugin to my system. So it's going to have its own API. So we use the adapter design pattern to then provide the interface. And so it does the translation between the core system's plugin API and the third party's API to then be able to use that third party API in my core system. So from the core system's perspective, it's something that conforms to my interface. And so it uses it the same way as every other plugin, but I've implemented my adapter that then does the translation from the core system's interface to the third party's API. And typically that third party service is then going to be an external service. So you'll have some communication protocol to talk to it. Oh, which leads us to a side note. When we start talking about complex architectures, we then start talking about ways of splitting it. So complex architectures have multiple parts. And one approach to splitting an architecture is based on your technology. So what is your infrastructure you're running on? And then optimize your architecture to the infrastructure. And your layered architecture typically is based on this technical approach, because we talk about the presentation layer and the business logic layer and the persistence layer and your data layer as your 4 common layers. And then that is commonly done that way because then, well, I can have my presentation layer running on mobile devices on a web server. I can have my business layer running on its own application server. Typically, persistence layer is going to be on that same server, and then I'll have my database running on the database server. And so we're structuring that layered architecture around the technology. So that's our technical partitioning. An alternative approach is what we call domain partitioning. And so domain partitioning is then we split the architecture based on things of interest in the problem area. So we commonly talk about the problem domain, and we identify what are the big things of interest in the problem domain and design our architecture around those problem areas or domains. And so an example, say from our Sahara e-commerce example, could be things like, well, things that are important to an e-commerce system is providing support for purchasing, and then fulfillment of purchases and orders, and then managing our inventory, and then managing customer accounts, doing all the data mining, generating reports, are all different potential things that are of importance. So you might design your architecture around those problem domains. And then just to keep life simple, we'll say, and they've all got a common database. But when we get further along, we're going to say, and we can split that database up into domains as well. So we said we design our architectures around either technical or domain partitioning. So does microkernel, and we said layered is technically oriented. Is microkernel technically or domain oriented? Would you use either technical partitioning or domain partitioning for a microkernel architecture? So if you were making your plugins associated with domains, you're going to use domain partitioning. But the core system itself could actually be partitioned in your layered or domain-oriented fashions, depending on how complex your system is. Yep.
So long that you can communicate with other others and be somewhat. That's sort of the thing that
so yeah, okay, so there's a question about, yeah, does that mean we could sort of have a layered architecture in our core system, which is not overly complicated, and so keeping within the spirit of the minimal core? Yeah, that's what we're trying to get towards. But it also introduces another thing, that if our core system is also partitioned by domains, that then actually adds an extra level of complexity, but flexibility to the microkernel architecture, because then each domain could have its own interface. So instead of saying the core system has one interface, each domain has its own interface. And if we're really lucky, some domains could share a single interface, which then just reduces our complexity of the core system. But that then provides us with this mechanism where I can have different domains in my application, and then different plugins that extend those domains. But some domains will need to pass different information and be working with different types of data. So we can then cope with that because each domain has its own interface. which is then, yeah, we introduced the idea of the layer and domain because we're going to then say, with a distributed microkernel, actually not an uncommon way of distributing a microkernel architecture is we use the technical layered partitioning within the core. And commonly it's going to be 3 layers that you'll have your front end, your back end, and your database as your 3 different layers. Just only put 2 on the slide because everyone knows about database and it wouldn't be readable if I put it on the slide. So we've got our 3 layers, which are based on the technical partitions that my presentation is in the front end, my business and persistence are on the back end, and then I've got a database server that the persistence talks to. And then I've got my plugins, which are then again specific to each layer. So I'm going to have my UI plugins, and then I'll have my business logic plugins. Okay. So what other types of systems? So we mentioned VS Code, IDEs, some operating systems, web browsers. What other types of systems could use a microkernel architecture? When we were trying to think of your tutorial, we had to sit down and think, but we did end up with close to a dozen. But a social media aggregator would be another one. You've got a very simple core. And then I could sort of say, okay, well, then here's my plugins for Instagram, Facebook, Snapchat, whatever. They pull data in and even then send data out. IoT. So I've got a bunch of devices sitting out there doing things, collecting data. So a home automation system or some data collection type system. This then works nicely because every time I add in a new type of device, it's just another plugin. And I've got a core system that just does the basic management. So basic management of home automation. So it's got a bunch of rules and alerts, and then the devices do things. And a media server would be another example. So we don't have time, but there is in the slides an example working our way through a microkernel architecture for a media server. And so I stole the architectures from Plex and Kodi and merged them together to come up with the example. Well, simplified and merged. Because Kodi, conveniently, someone's already written an architectural description for Kodi. Plex, I know the architecture for because I contribute. But they do things differently. So that's why merge and simplify. But the idea, you want to have a media server and want to have a single server. It's got its database, it's got its access to your media, and then I want to have renderers all over the place. So I can render on my phone, I can watch on the phone, I can have it on my home theater system, I can watch on my computer. So those are my renderers. The design is going to use domain partitioning. So that color code just tells you what the different domains are. So things to manage audio, video, managing your library, navigating through your library, user interface, and other core logic. And so we're also going to distribute this, which the first diagram implied. So your renderer is one device, your server is a separate device. So I've got a simple-ish core system for rendering. And I'm going to have UI plugins, which are going to provide me with my basically user experience and skins. If I wanted to make this more complicated, we would actually have plugins for video and audio. So that way you could then have customization of what streams you deliver to your renderer. And then it talks to the library. And so core rendering system has simplistically 4 basic components: play video, play audio, the user interface, and the registry of the plugins. And if I was going to then say I'll have audio plugins and video plugins, I'd probably have separate registries for those, just to make it easier in my design. Media server then has plugins for streaming and audio, because on servers where I'm actually going to do all of my transcoding from different codecs and reformatting so that I can deliver stuff that my renderer can actually consume. And then I'm going to have stuff for scraping media and actually populating my database and navigating through all of the library that I've got available. And so it's going to have components to manage that as well. And then the renderer talks to the video and audio streaming and library navigation to actually do its rendering. And then I have plugins for all of those things. So I have plugins for the library management, so it can talk to all sorts of different ways of scraping metadata for my library. I'll have plugins for navigation to do custom navigation, because I can then say, well, audio video is easy, but what happens if it's home audio versus so home movies that people have recorded versus commercial movies that they have ripped from their Blu-rays. And so I'm going to want different ways of navigating different types of similar types of media. Video streaming plugins, audio streaming plugins, so I can have all of my different types of codecs for managing all the different types of media formats I might be working with. And if you look at the C4 model, which is on the course website, you can go dig your way through, and there is then examples of plugins for each of the plugin containers. And then there's an example of your scrape interface, which again is simplified. But yeah, it's got scrape some data from somewhere. I don't care where, because each of my plugins will implement that interface and implement how they actually do the scraping for their particular data source. And all they need to know is what's the data I want for this particular type of media, and then they return the appropriate metadata. And so I'll have a metadata object and a media data object, which is how we pass the data from the core system to the plugins. And then we'll deploy that. So I'll have renderer running on one type of device, server running on another device. Commonly with media servers, then your file system and database are actually on the same device as your media server, but we could have fun and put them elsewhere. Both Plex and Kodi actually cope with putting the file system elsewhere. Kodi does not cope so well putting the library database elsewhere. So microkernel. Got a reasonably simple design for your core, simple interface to your plugins. Each of the plugins focus on a single task, so they're nice and simple. They're extensible via plugins, and you can have as many plugins as you want. Plugins provide interoperability with other systems because they provide that way of adapting to talk to any other system without core system needing to have any changes. Moving on, we're going to be looking at scalability and reliability as quality attributes later. There are going to be some issues when I want to try to scale up a microkernel architecture, and reliability, there's going to be some issues there. But simplicity, extensibility, interoperability, modularity are all things we get with microkernel. Any questions? Yep.
But then there's the plugins provide extensions functionality to the core systems directly, or
Yep.
does it provide another interface for the external users to like communicate?
Okay, well, from the conceptual perspective, we think of the plugin provides the extensibility by implementing new functionality that's added into the core system. But then, yeah, it could implement that by just actually being the adapter that says someone else really does it. And I just do whatever internal translation is required.
And then my second question is like, what's the difference between the microkernel architecture and then microservices?
Ah,
Because
okay.
through like the diagrams, it seems.
Ooh.
Similar.
It's amazing how similar these diagrams get for very different architectures. So, okay, we will talk about microservices in detail towards the middle of the semester because we're going to talk about a couple other things before we get there. Some of the key things are microservices focus a bit more on isolation between things. And basically, they're getting rid of the core system and just having a bunch of services rather than plugins to a core system. So it's trying to get rid of this central hub that becomes a scalability issue with microservices. So microservices try to keep the services as independent as possible so I can scale the system as an entirety much better. But yeah, we will be talking about microservices actually in a fair amount of detail. And we will be getting in a couple of experts on building microsystems and who've built some of the sort of key libraries used in designing microsystems or microservices to look at that.